Hello, I am just a smidge behind. This is the wrap up for fractions. We are wrapping up fractions, everything from finding the prime numbers, or finding prime numbers, composite numbers, 0 and 1 being neither of those, and what have you. Let's get this situated. All right, that'll do. I think that is here. Let me switch this back just a bit. We will cut out the blurring. We should be just about there. Sweet. Okay, switch it back. Here we are. Okay. Yes, we're going to go over what we have been talking about with fractions from the very beginning, starting with the first bit we know about prime numbers. Which are any whole number that has exactly two factors, one in itself, that is very important, and where we have a prime, there we go. We also have composite numbers. Getting my syntax correct. Composite number, any whole number greater than that is not prime. Very cheap and easy definition. Whereas 0 and 1 are neither prime nor composite. So all numbers, all positive whole numbers are either prime or composite, except for 0 and 1, which are neither prime nor composite. And we haven't gone over why that is, because anything times 0 is 0, and this could be done for any number of factors other than 0. So you can do 1, 2, 5, and so on. And they would all equal 0. So that makes it not prime because it has multiple factors, but it's not composite necessarily because the other factor is still 0. Because this factor does not change, that makes it a technicality. It makes it a bit complicated. Whereas 1 times 1 equals 1. Sure, those are just the two factors of 1. So arguably it's prime. But the only two factors, except 1 times 1 times 1 times 1 times 1 forever and ever, will equal 1. So it's not just the two factors which would make it prime, but only 1 times itself any number of times would be 1. So that's not necessarily composite either. All right, we had gone over all the divisibility rules. I say all. We have gone over divisibility rules for 2, 3, 4, 5, 6, 9. I believe these are the only ones we've gone over. So it's divisible by 2. Its last digit is 0. 0, 2, 4, 6, or 8, or otherwise that number is even. If it is divisible by 3, personally, this is my favorite way to discern if it's divisible by 3 because it's kind of unintuitive. Why would you look at a number this way? Only to discern if it was, in fact, divisible by 3. So if it's divisible by 3, the sum of the digits is divisible by 3. So in the case of so if we have an example, 126, we can discern that 12 and 6 are both divisible by 3. However, 1 plus 2 is 3, 3 plus 6 is 9, and 9 is certainly divisible by 3 with 3. So we wouldn't have to divide the initial number by 3 to discern if it was divisible or not. If it is divisible by 4, the last 2 digits of the number is divisible by 4. So no matter what the rest of the number looks like, if the last 2 digits are divisible by 4, then the entirety of that number is divisible by 4. Such as if we have 1, 3, 7, 25, or 24, then 13,724 is divisible by 4 because the 24 is divisible by 4. If we are divisible by 5, the last digits is either 0 or 5. Because, mercifully, in our decimal-based number system, 5 is the halfway point. Because we have 10 digits, and 5 would be half of those. So 5 and 5 is 10, 5, 5, and 5 is 15, 5 more would be 20, 25, 30, 35, 40. It's a nice intermediary to which we have 0 and 5 alternating. So if a number ends in 0 or 5, it is divisible by 5. So we have divisible by 5, divisible by 6. It's divisible by 6 when it is divisible by both 2 and 3. And we have tested 2 and 3 out with previous rules. And if it's divisible by 9, very similarly to being divisible by 3, the sum such as we had that number 126, whose sum was 9. 1 plus 2 plus 6 is 9. That is divisible by 9, so 126 is divisible by 9. All right, so that was the breakdown of numbers in section 1. We have factorization, or factors of whole numbers, in which case what is interesting to know is prime factorization. Is wherein, for example, we are given a number 630. The prime factorization is to find the prime factorization of a number is to divide the number by a series of primes until the final quotient is a prime number. Or you can do the tree method. Either way, it'll derive the prime factorization, which is unique to every number. So 630, as described by the initial way, let's divide it by 3, since 6 and 3 is 9, and 3 is prime. We have 3 can fit into there 210 times. So then 210 is again divisible by 3, can fit into there 70 times. 7 is prime and can fit into 70 10 times. 2 can fit into 10 5 times, and each one of these is prime. So the prime factorization is 2 times 3 times 3 times 5 times 7. So 2 times 3 times 3 times 5 times 7. I like to put it in order because it's nice and neat that way. I know a lot of papers would like them to be in quantitative order. And because we have 2 of the same characters here, or 2 of the same values, multiplying, we can 2 times 3 squared times 5 times 7. Now, the tree method, you have made discerned. We have 63 times 10, and you just break it down to as many primes as you can until you cannot break it down any further. So 63 and 10, pretty straightforward. 63 is of 9 and 7. 7 is prime, 9 is 3 and 3, and these are prime. 10 is 2 and 5, which are also prime. So the same fruits of this tree are the same as the multiple division. Going forward, we understand the definition of a greatest common factor, or GCF, as it is the largest number that is a factor of each in a group numbers. Now it says in a group, most of the time we're looking for between just two different numbers, but you do need to know in the case of like 3, 6, and 9 that the greatest common factor, 3 is 3 times 1, 6 is, let me see, 6 times 1, and 2 times 3, and 9 is 1 times 9, and 3 times 3, which would just be 3. And the only number that is the greatest, or that is similar between them, is 1 and 3 is the bigger of the two. So that makes it the greatest common factor in this particular set. So that is discerning the list of factors or you could take the prime factorization of each one. So we just have we have 1 times 3, and 6 we have 1, and 6 is 2 times 3, and 9 is 1 times 3 times 3. 1's not necessarily a part of the prime factorization. We just have it here just in case they had nothing else in common. And we see that they have all 3's in common, but they have just the 1's in common, so nothing else in common. So then we multiply that. 1 times 3, the greatest common factor, 1 times 3 is 3. I believe I said it when we first went over it that prime factorization is the fastest way to find the greatest common factor. However, if you need to list out the factors, each and every one, you are allowed to do that. You can do that. It will take more time to do so. So we understand the fraction basics, generally, that a fraction names a number of equal parts of a unit or a whole. A fraction is written in the form a over b, in which a and b are whole numbers and b cannot be 0. So, verbally speaking, this illustrates, and please assume that I've drawn this in due scale so that it's nice and even. So we have this whole, pi, or tire, or what have you, and we will shade in 4 pieces of it. So there are 4 pieces shaded, and there are 6 pieces in all. So this would be the fraction of the pi tire circle that we have. Where this is our numerator. This is our denominator. Yeah. Numerator's on top, denominator's on bottom. Denominator denotes what we are talking about, so it denotes the entirety. The numerator numbers off what portions we have. Okay, and just so that you may have it for reference, the definition of a fraction So where a and b are whole numbers and b cannot equal 0. This, simply stated, means we can't have nothing that we cut into pieces. We have to have something to cut into pieces. There is a more complicated reason as to why that is, but that's more of an algebra problem that we are not there yet. So a proper fraction, such as, say, 5/6, is one whose numerator is less than the denominator, and it is less than 1. So 5 is smaller than 6, and this does not equal 1. It does not greater than 1. So this would be a proper fraction. Compared to that, we have an improper fraction, such as 6/5. That's where the numerator is greater than the or equal to the denominator, such that 6/5 can also be rewritten as 1 1/5, which is a mixed number. Also, we see 7/7 is an improper fraction because 7 can fit into 7 once, and that is exactly 1, not necessarily a mixed number. So this is a whole number, not a mixed number, but this is still an improper fraction. Changing from a mixed number to an improper fraction and back, say we have 22/5, so we have an improper fraction. We are changing to a mixed number. 5 can fit into 22 4 times, with 2 remaining. 2 is smaller than 5, so that would be our remaining fraction. And to change it back into an improper fraction from a mixed number, 4 times 5 is 20, plus 2, with that denominator of 5, so 22/5. Since we have fractions, we can simplify fractions. So if we are given an example of 4/6 to simplify, we have 4/6, and between the two of these, they have a 2 in common. This is more of an inherited thing where you can just look and see, but if you need to, prime factorization, as we have done before, 4 is 2 times 2, 6 is 2 times 3. They have this 2 together, so that can cancel out. So this reduces or simplifies to 2/3. All right. So we have something that is a cross product. I don't know if I said it verbatim before, but a cross product is when you have some fraction, let's say 2/3, equals 4/6. A cross product checks to see if they are equivalent. So a cross product is when you take the numerator of one multiplied by the denominator of the other, so that'd be 2 times 6, leave that equal sign there, and the denominator of the first times the numerator of the second, 3 times 4, 2 times 12, or 2 times 6 is 12, and 3 times 4 is 12. Since they are the same, they are equivalent. An equivalent is when one of them can reduce to be the other, essentially, in some form or fashion. So we know how to simplify. There's a phrase called simplest form. That simply means if you're given a fraction and you can simplify it to another fraction, but you cannot simplify this other fraction any further, that is the simplest form. It's pretty straightforward with that definition. And then multiplying fractions and dividing fractions. As we were building up to this entire chapter 4, so we have 5/8 times 3/7. And look before you leap. So we have 5/8 and 3/7. Nothing reduces. You can multiply straight across. So that would be 5 times 3 is 15. 8 times 7 is 56. Nothing reduced here, so nothing can reduce there. This is in its simplest form. We also have the example of 5/9 times 3/10. And here we can notice that the 5 and 10, being a numerator and denominator, they can reduce. 5 can fit into 5 once. 5 can fit into 10 twice. In between 9 and 3, we have a 3 in common. 3 can fit into 3 once. 3 into 9 3 times. And now we can multiply with what is remaining. 1 times 1 is 1. 3 times 2 is 6. And dividing fractions uses what is called the reciprocal. So given an example of 3/7 divided by 4/5, the reciprocal, we will use the divisor to find the reciprocal. So the reciprocal thereof, since this is 4/5, it will be 5/4. And so dividing by 4/5 means to multiply by the reciprocal 5/4. So 3/7 times 5/4, which we've seen multiply straight across. 3 and 5 is 15. 7 and 4 is 28. None of which reduced, so nothing can reduce. It's in its simplest form. So if we were given 6 and 2/3 divided by 1 and 3/5, first we have to translate these, transform these, rewrite these into improper fractions so we can work with them. 6 times 3 is 18, plus 2 is 20, over 3, divided by 1 times 5 is 5, plus 3 is 8/5. And since we have the divide, we will multiply by the reciprocal of 8/5, so that would be 5/8. Check to see if anything reduces. The 20 and 8 both have a 4 in common. 4 can fit into 8 twice. 4 can fit into 20 5 times. Multiply across with what is remaining. So 5 times 5 is 25. 3 times 2 is 6. This is an improper fraction, which can be rewritten as 6 can fit into 25 4 times, which is 24 from 25. with 1 remaining, and the denominator of 6. That is to say, 1 3/5 can fit into 6 2/3, 4 1/6 times. Neat. And I believe that covers the review. Going forward, we will simply do examples. I believe so. Chapter 2. All right. And we will do all of what we can of the review questions for this chapter. So, number 1. Which of the numbers are prime numbers? We are given 5, 9, 13, 17, 22, 27, 31, and 45. Now, which ones are prime? It is easier to find a prime by getting rid of composites. So 5, 2 cannot fit into 5, 3 cannot fit into 5, 4 cannot fit into 5, 5 can fit into 5, but only with 5 and 1. So 5 is prime. 9 is divisible by 3, so it is not prime. 13, not divisible by 2, 3, 4, 5, because it's not divisible by 2 or 3, it's not divisible by 6, not by 7, not by 8 or 9 or 10 or 11 or 12. It is only divisible by 13 and itself, which is itself times 1. So 13 is prime. Same for 17. Not 2, 3, 4, 5, 6, or 7. 8, 9, 10, 11, 12, 13, 14, 15, 16, or just 17. So 22, we see that the last digit is 2, which makes it divisible by 2. So it is not prime. 27, we can see that 2 plus 7 is 9, which is divisible by 3, which means not prime. And 31, going through, it's not divisible by 2 or 3 or 4 or 5 or 6, not 7. It's not even, so it's not going to be divisible by 8, 10, 12, 14, 16, 18, or 20. Let's see. Other than that, I don't think it's divisible by 29, so 31 is prime. And 45 ends in 5, so it is divisible by 5, so it is composite. So the remaining 5, 13, 17, and 31 are prime. All right. Determine if 2, 3, or 5 are factors of 54,204. So to determine if it's divisible by 2, we know the last digit must be even, and it is, so it is divisible by 2. If it's divisible by 3, the sum of these digits is divisible by 3. 5 and 4 is 9. 10, 11. 11 plus 4 is 15. 15 is divisible by 3, so it's divisible by 3. And to be divisible by 5, the last digit must be a 0 or 5. It is not, so it is not divisible by 5, so it is divisible by 2 and 3 only. And find the prime factorization for 264. So in the tree method, I can see that this is divisible by 4. So we have 4. Get into 26, 6 times, and again. So this is 11 and 6. 11 is prime. 4 can break down to 2 and 2, which are prime, and 6, 2 and 3, which are prime. So we have 2 times 2 times 2, which is 2 to the third, times 3 times 11. We could also have 264 divided by the prime 2, 132, which is divisible by 2, which is 66, divided by 2, 33, divisible by 3, which makes an 11 up here. So 2, 2, 2, 3, 11. 2, 2, 3, 11. So we have, for numbers 4 and 5, find the greatest common factor for the given numbers. So 4, we have the numbers 36 and 84, which we are going to find the prime factorization and compare and find the greatest common factor. So 36 is divisible by 3, so that is 12. 12 is divisible by 3, and 4 is 2 and 2. 84 is divisible by 2, which would be 42, also divisible by 2, which would be 21. 21 is divisible by 3, and 7. If need be, multiply all these back up to verify that they do in fact equal the number that you found them for. So 3 times 3 is 9, times 4 is 36, 2 times 2 is 4, times 3 is 12, 12 times 7 is 84. So we see they have a 2 and 2, 2 and 2, a 3 and 3, but nothing else in common. So the greatest common factor equals the 3 times 2 times 2 is 12. Five. We have 16, 24, and 72, to which the prime factorization is 16, 2 and 8, 8 is 2 and 4 is 2 and 2, 1, 2, 3, 4, 1, 2, 3, 4, 24 is 4 and 6, 4 is 2 and 2, 6 is 2 and 3, 1 times 2 times 2 times 2 times 3, and 72, which is 8 times 9. 9 is 3 times 3. 8 is 2 times 4, and 4 is 2 times 2. So then we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. They all have a 1 in common, but all numbers do. They have that 2 in common. They have another 2 in common. They have another 2 in common. And that is it. They just have 3 2's in common. So the greatest common factor is 2 times 2 times 2, which is 8. Okay. So, number 6, 7, and 8 ask what fraction names the shaded part of each diagram. Identify the numerator and the denominator. So number 6 shows us a circle, not an oval, with 6 pieces, 5 of which are shaded in. So again, it has 6 pieces, 5 of which are shaded in. The 5 is our numerator, the 6 is our denominator. 7, we are shown to have a rectangle with 5 pieces shaded out of 8, where 5 is our numerator, 8 is our denominator. And 8, we have 5 bubbles, 3 bubbles are shaded in, so 3 of the 5, where 3 is our numerator and 5 is our denominator. So 8, 9. 9 asks to identify the proper fractions, improper fractions, and mixed numbers of the following group. So we are given 10 elevenths, 9 fifths, 7 sevenths, 8 oneths, 2 and 3/5, and 1/8. So this is a proper fraction. As we have previously defined, the numerator is smaller than the denominator. 9/5 is an improper fraction because the numerator is greater than the denominator, as is 7 sevenths. Where they are equal, it can reduce to 1. Again, this is an improper fraction. This, however, is a mixed number because we have both a whole number and a fraction. And we have 1/8, which is a proper fraction. And rule of thumb, if you use abbreviations in your answers, please write out what they mean for people who have to go and grade your answers. Because just because we went through and we talked about it, it doesn't mean if I hand this paper to someone, they know what these abbreviations mean. So, since I have had to use pretty much each of them more than once, for clarification. Number 10 asks, give the mixed number that names the shaded part of the following diagram. So that simply means of 1, 2, 3, 4, 5. They're given 5 circles, 4 of which are completely shaded, In the last one, one piece out of 4 pieces are shaded. Two. 11, 12, 13, and 14 asks to convert the fractions to mixed or whole numbers. So 10, we are given, or excuse me, we just did 10. This is 11. 11 is 17 fourths. 4 can fit into 17 4 times, with one piece remaining. Get a mixed number for that. 12. We have 74 eighths. 8 can fit into 74 9 times, with 2 pieces remaining. But 2 over 8 can reduce. So that'd be 9. They both have a 2 in common, so it's a 1 and a 4. 13. We have 18 over 6. 6 can fit into 18 exactly 3 times. 14, we have 15 divided by 1, or 15 oneths, which is simply 15. We are a little short on time. I'm going to go ahead and skip the remaining reductions and rewriting into simplest form to multiply and divide problems. So we can make sure we have reiterated exactly what we came into this chapter to do. So we have number 27. Which multiplies 2 over 3 times 5 over 7. Nothing reduces. 2 times 5 is 10. And 3 times 7 is 21. 36. We have 6 sevenths divided by 3 fourths. Because we have a division, we can multiply by the reciprocal. So 6 sevenths multiplied by 4 thirds. The 6 and the 3 can both reduce. 3 can fit into 3 once. 3 can fit into 6 twice. So now we may multiply across. 2 times 4 is 8. 7 times 1 is 7. This is improper, so it can be rewritten as a mixed number. 7 can fit into 8 1, with 1 remaining. 27, 28, which has 9 tenths times 5 eighths. The 10 and a 5 can reduce, as a 5 can fit into 10 twice, 5 can fit into 5 once. 9 times 1 is 9. 2 times 8 is 16. We're given 7 twelfths divided by 14 fifteenths. So then we have 7 twelfths multiplied by 15 fourteenths. This reduces quite a bit. 7 and 14, they reduce each by a 7, so 1 and 2 respectively. 12 and 15 have a 3 in common, which reduces to 4 and 5. Multiply across with the remaining. 1 and 5 is 5. 4 times 2 is 8. And that is a proper fraction in simplest form already. 29. We have 2 2/3 times 1 2/7. Transcribe them into improper fractions first to be able to work with them. Okay. 2 times 3 is 6, 7/8. Thirds times 1 times 7 is 7, 8, 9. Sevenths. The 3 and 9 can reduce. 3 can fit into 3 once, 3 into 9 3 times. Multiply across with the remaining, so you get 24 divided by 7, which is improper, to be rewritten as the mixed fraction. 7 can fit into 24 3 times, with 3 pieces remaining. $38. We have 1 3/4 divided by 1 3/8. Rewrite as improper fractions to work with them. 1 and 4 is 4, 5, 6, 7 fourths divided by 1 times 8, 9, 10, 11, eighths, multiplied by the reciprocal, which would be 8 elevenths. The 4 and 8 can reduce. 4 can fit into 4 once, 4 can fit into 8 twice. Multiply across. 7 times 2 is 14. 1 times 11 is 11. This is improper, to be rewritten as 11 can fit into 14 once, with 3 pieces left over. We have time for one more problem, and then I will call this done for this chapter. Multiplying and dividing fractions. So 29 and 30. It's 30. 30, we have 3 and 5/6 times 2 and 7/5. 18 plus 5 is 23. Fun fact, 23 is prime. 2 times 5 is 10, plus 7 is 17, also a prime number. 23 and 17. Let's see. That's 230. 740 and 21. 1, 3, 7, 9. That's 391 divided by 30. This is an improper fraction. 30 can fit into 391. How many times? $13 times, with 1 piece remaining. All right. Now, I believe going forward, get a decent grasp on multiplying and dividing fractions, knowing how to find the greatest common factors. And so going forward, the next chapter we will get into is addition and subtraction of fractions. We will revisit this not next week. What shall we do? We'll go over the pre-test for this Thursday to kind of give an overview of the entirety of what addition and subtraction of fractions will incur. However, we will not go into depth for, I'm going to say, at least 2 weeks. So, what does that mean? So, we will go over the test, the pre-test, August 10th, this Thursday at 6 p.m. We will not reconvene again till the earliest, August 29th at 6 p.m. And that indeed is subject to change, and I will keep you posted if it does. Otherwise, if you have any questions, comments, concerns, emails, if you need, let me know. I'll get back to you as soon as I can. Bye.